So the Fourier transform is an integral transform similar to the Laplace transform, but better suited to the entire real line. So what we'll see is that Laplace is best for semi-infinite domains, and then Fourier transforms are better for working on the entire real line, and then Fourier series are best for working on bounded domains, so compact intervals. So the definition, the Fourier transform takes a function u of x and transforms it into some function u hat of the new variable xi. And this is defined as the integral over the entire real line of ux e to the I xi x dx. And so here xi is a real number, but in general u hat can take complex values because of this these imaginary numbers in the integrand. And so the kernel for this integral transform is e to the I xi x. And this, since we have that xi and x are both real numbers, this means that by Euler's formula, we have cosine xx plus I sine xx. And so this integral kernel, e to the xx, is actually a unit complex number. So these are the, so here's an e to the I xx. And so you should think of this in terms of frequencies. So these are the coefficients in front of the x. So these are frequencies. And so if you consider this as e to the I xi raised to the power x, which it equivalently is, then basically the role of xi here is xi tells how many cycles you make. Whoops. As x goes from 0 to 2 pi going around the circle. Okay, so one of the nice things about the Fourier transform is that the inverse transform is relatively simple. It's less difficult to deal with, for example, than the inverse Laplace transform. And so we recover u from u hat by doing essentially the same thing. Now there's a normalizing factor of 1 over 2 pi. But then, and then there's also an e to the, there's a negative sign in the exponent here. But otherwise, it's just basically exactly the same. And depending on the book that you're looking in, some books will preface both of these with a factor of 1 over square root 2 pi so that it looks more symmetric. Our book has chosen to put the 2 pi entirely in the inverse transform, just something to be aware of if you look at another book somewhere. So the Fourier transform has a similar property to the Laplace transform in that if we take the transform of the derivative of something, then it's going to convert that differentiation into multiplication by the independent variable, or in this case, minus I times the independent variable. And again, that comes by doing integration by parts. And so for the Laplace transform, we can usually avoid the fact that we're secretly working in C, because the transform variable S is actually secretly a complex variable. It's just that with most of the applications and the way that we use it for solving differential equations, we can dodge around it. Two exceptions to that are when you look at things defined in terms of integrals. So in particular, the inverse Laplace transform is a contour integral in C that is necessarily going to be complex. And then also, we talked about the way that the Laplace transform of a convolution is equal to the product of the Laplace transforms, but it also goes the other way. And so that is, if you have f times g, this is going to be this is going to correspond to the, well, actually here, L of f times g is going to be the convolution of f and g. And the integral defining this convolution is necessarily going to take place in the complex plane as well, which is why, for the most part, we just completely skip that. If you go look at your notes from your last Laplace transform class, probably they didn't do this one at all. You just stuck with this one. So let's see. So if so the Fourier transform of u is defined whenever the absolute integral of u exists and is finite. That's the basic case. So for Laplace transforms, we required that the functions be piecewise continuous and of exponential order. For Fourier, we require this condition. And so this condition, in order for the integral not to blow up, you need it to be the case that the integrand is going to 0 as x goes to positive or negative infinity. And it has to go to 0 sufficiently quickly that the integral actually converges, right? There are lots of functions with fat tails. So, for instance, they tend to 0, but not fast enough for the integral to converge. So, for instance, 1 over x, right? So let's see. So then most of the time we talk about a particular class of functions that's nice. So the Schwartz class, that's what the S is for, refers to smooth functions that vanish faster than anything of the form 1 over x to the power n. And actually, this is a slight lie. I said smooth functions that vanish. I should have said smooth functions, all of whose derivatives vanish faster than any power like that. So to make this more precise, so this is going to be all C infinity functions. So C infinity here, a function is called C infinity or said to belong to the class C infinity. You can differentiate it arbitrarily many times. No matter how many times you differentiate it, you get another continuous function. So all of the smooth functions that have the property that if I take any derivative, so like the kth derivative for any k, then this is going to be bounded by some constant times 1 over x to the n as x gets large. And so this is for any derivative of u, including the 0th, which is u itself, and for any integer n. And okay, so again, this is a discussion in terms of what it looks like for single variable functions. We also can apply it to a function of 2 variables. And in this case, we usually do it to x. So then the result is going to leave t in place doing whatever it does. It's defined as the integral of uxt e to the ixx dx. And by the same properties that, or the same calculations that we saw before for Laplace transform, the Fourier transform of an x derivative is going to kick out a factor of minus I xc. But the Fourier transform of a t derivative is going to be completely unaffected. So we just have u hat t.